Okay, it's time for a new concept, and we're going to use de Moivre's product theorem, which we've talked about before, to come up with a new theorem called the power theorem. The power theorem talks about how you raise a complex number to a certain power, 3, 4, 5, whatever. And what I want to do is start off with the product theorem and say, if I have some complex number z, and we're going to say theta equals theta z. Okay, that's just what it is. Now, what if I said z squared? Well, that's z times z. So according to the product theorem, what you do is you add these angles together, and you get 2 theta z. Okay, 2 times theta z. Great. What if you multiply again? Well, you're just going to keep on adding these angles together. Now you've got 3 of them because you have 3 powers of z. So that becomes 3 theta z. And you can see the pattern that's going to develop. Regardless of what power you raise this to, it doesn't get any harder to find this angle. All you do is you multiply the angle times the power. Okay, so if I raised z to the 10th power, then I would just multiply the angle by 10. This is the power theorem right here. Okay, so let's see how that applies to a problem where we're trying to put z squared, z cubed, z fourth in rectangular and polar form and put them on this graph. See how it comes all together. First step though, preliminaries, we've got to know what the magnitude or the modulus of z is, and I need to know what the angle of z is. So you remember modulus is found by the square root of real part squared plus imaginary part squared. And if you work through the math on this one, you will find that equals 2 in this case. The theta value, I always like to spend a little more time on this because it's a tricky one. Theta, if you do this imaginary part divided by this real part, you'll get 1 over radical 3. So the question is, where is tangent equal to 1 over radical 3? Well, there's 2 places. 1 is right here, okay, at pi over 6, and 1 is over here at 7 pi over 6. In both cases, if you take the tangent of that angle, you will get positive 1 divided by radical 3. So which one is correct? Well, here's where you have to use quadrant information. And as I'm looking at this z, I see a positive real part and a positive imaginary part. That means I'm going over and up. Okay, so I am in quadrant 1. We can forget this quadrant 3 stuff. So here's where I am, pi over 6. So it's going to be pi over 6. And now I'm ready to write this in polar form. This part's easy. You just say the modulus times the cosine of that angle plus I times the sine of that angle. And now it really is so easy using the power theorem to go all the way down the line here in terms of polar forms. If my modulus is 2, you know what? I made a mistake earlier. That modulus is not 2. That is square root 2. Sorry about that. So my modulus is square root 2. Now, what's that squared? Well, square root 2 squared is going to be 2. And what else happens? Well, remember what we do to the angle. If you square z, that means you double the angle. So this becomes 2 pi over 6. No problem. 2 pi over 6 right there. And then what happens if I cube z? Well, this is going to be radical 2 times radical 2 times radical 2. That'll be 2 radical 2 for the modulus. And the angle is now going to be cosine of 3 pi over 6. And I sine of 3 pi over 6. Okay, so we just tripled the angle now. And it'll be the same for the 4th power. That'll quadruple the angle. So let's just get that on here so we can have this complete. This is going to be a modulus of 4 times cosine of 4 pi over 6 plus I times sine of 4 pi over 6. Now, plotting these things is pretty easy. I think maybe the hard part, if there is one, is plotting the modulus correctly. Square root of 2 is about 1.4. So this first point I would put somewhere like this. Okay, that's at pi over 6 with a radius of 1.4. And the second one, let's get this in blue, that's going to be a radius of 2 at 2 pi over 6, or in other words, pi over 3. So that'll be right here at this point. Okay, that next one, which is, I've got this in red, that's 2 radical 2. So that's 2 times about 1.4, 2.8, right? It's almost 3, which makes sense. It's the square root of 8. That's almost the square root of 9. So there's my modulus and my angle right here for the cubed power. And the fourth power of z, I've got this in magenta, we're going to continue rotating by the same pi over 6 angle every time. And now the radius has gone out to 4. So you see, every time you increase this by another power of z, what's happening? Well, you're scaling it by a factor of radical 2. It's not a big increase, but it is building up over time. And the counterclockwise rotation is going by that angle of pi over 6. And you can see this. This thing's getting longer, and it is going counterclockwise. Now, in terms of the rectangular coordinates, I haven't filled those out, but this part is really quite easy. All you do is you evaluate this deal in parentheses. So the cosine of 2 pi over 6, for example, is 1/2 times 2. That becomes 1. And the sine of 2 pi over 6 is radical 3 over 2 times 2 becomes radical 3. So this becomes 1 plus radical 3i. Okay, that's my radical form there. And now for the next one, what I would do is I'd say, okay, what's the cosine of 3 pi over 6? Well, that is 0. So you can say 0 plus if you want, or you could just leave that part blank. It doesn't matter. Sine of 3 pi over 6 is 1. So this just becomes 2 radical 2i. Okay, and so on. The rectangular forms, once you have the polar forms, it's pretty easy to get the rectangular forms. You just evaluate it.